Okay, thanks. All right, so before we start today, a few things that I left out last time that are important. I believe we said we're going to deal with Newtonian mechanics, which means that time is the independent variable, and it doesn't matter which reference frame you are. Time is going to tick for you at the same rate. This is also called Galilean invariance. It's always good to credit people for what they do. Galileo Galilei, very smart guy. We only shared the nationality. He was much smarter than I am, but he's one of those guys who came up with very important and basic concepts. We'll consider them basic concepts now, but they are foundations for everything we do today. We couldn't be engineers without these people, to be honest. Couldn't have cars, airplanes, spacecraft. All we do, it's because of them. So that's what it's called. The other point that I wanted to make, and I actually sent you an email about that, and if you guys don't get my emails, you should let me know. I think everybody should be in the distribution list at this point. At some point, I took my reference frame, the box, which, by the way, it's gone. Someone stole the reference frame. And I taped the vector, which is still here, to the reference frame, and I moved it around, and I said, this is constant in that reference frame, which I called A, and I said dB in dt in A is going to be equal to 0 in that case. The only point for doing this was that along the line, I said, well, the same is valid for a coordinate system, for the basis of a chosen coordinate system, which is fixed in that frame. It will still be taped to that frame. So we went to saying that dEI in dt in A is also 0 for I equal to 1, 2, and 3, assuming that, of course, E1, E2, E3 is fixed in A. And then I moved on and actually went back to the case where B is a generic vector that actually is changing. So one of you guys came after the lecture and said, well, is it B changing or not in this reference frame? Well, erase this if you like. This is where I wanted to go. Just saying that a vector which is fixed in reference frame, of course, doesn't change in the reference frame. So B for us is a generic vector that can change. I just called it B. I could have just called it EI right at the beginning. So I thought that was a little confusing because then I allowed B to change for my following steps, and that's what we'll do. Okay, so these are the communications. One other email that I got from one of the students was about homeworks. As the syllabus states, I'm not going to assign homeworks, meaning I'm not going to give you problems. You're old enough to navigate a book and find the things that I'm talking about here and corresponding problems. What I can do, I can tell you every once in a while what is the next problem that I'm going to solve if I'm planning to give you an example. So you try to solve it yourself first. That would be one way. The other way to do it, if you really want me to choose problems, come to office hours. I have to give you incentives. You have to either do it yourself in terms of solving problems, or you come to office hours and then we'll solve problems together, or I'll pick some problems for you from the book. That works as well. So that's the life of the graduate student. You need to actually start opening the book. Okay, so today we're going to continue from where we left off, which was this expression here, d dt of B in a reference frame A equals, let me write the entire formula here, dB1 dt E1 plus dB2 dt E2 dB3 dt E3 plus B1 d dt in A of E1 plus B2 d dt in A of E2 plus B3 d dt in A E3. Remember E1, 2, and 3. Now it's fixed in B. These are just names that I give to reference frame. A, B, C, doesn't matter. The point is that I am in B. I can express the vector in B. I can measure its rate of change in B. This is what I can do directly, right? I am sitting in B. So this is d B dt in B. That I can measure. But I would like to know what my friend in A sees, and this is the difference between the two. So this first part, we all understand, I hope, and agree that this is what it is. This is what you measure directly. This second part, we can write it in a better way, as we will do today, defining the angular velocity vector, which is the big monster, or I guess the huge elephant in the room usually. People don't really know what the angular velocity is, or they make wrong assumptions usually. So we'll try to be a little formal and definitely correct in what we're doing. Before we do so, I need to touch on some other refreshers here about vectors, things that you should know, but I want to refresh anyways. Everything we do when we add vectors, for example, in the algebra of vectors, subtract vectors, etc., cross products, and so on and so forth, it's done on what kind of vectors? There are three types of vectors that we can define. The most general one is the one that I have been calling all the time just vector. Well, at least I assumed so far. But there are three vectors, and that's a family of vectors, right? And that's what you use when you add vectors together, when you do cross products, when you subtract vectors. Every operation that you do that involves more than one vector is on three vectors. You can't add two vectors unless you move them and you do your triangle. You have to do that. So definition of free vectors is the following: B and let's call it B prime are the same free vector if they have the same magnitude and direction. Again, this may seem obvious, but it's important. You need to know which kind of vectors you're using and what you can and cannot do with them. So for example, what are free vectors, examples of free vectors? So first of all, if this is my vector and I move it around without changing its orientation, these or down here, they're the same free vector as far as I'm concerned. Well, an example is what we just defined last time. If you have your origin, which is fixed in A, so you have a reference frame A, you pick O fixed in A, which is this point down here, and then you define your coordinate system, defining a certain basis, E1, E2, E3. And let me be consistent with what we're doing today. Today we're fixed in B. I just don't want to confuse people. I just write A because I want to indicate a frame. Okay, so I have an origin, I define the three vectors. They don't, we always draw them this way, but they don't need to be originating, have a point of application, it doesn't matter. I can put E1 down here. So when you're solving your problems, if it's more convenient for you to move them around, you can. It's the same basis. I can still write B as B1, E1 plus B2, E2 plus C3, E3. That's an example of free vectors. I think I can actually erase these. Yeah. I'm not going to use it. Then we start adding constraints, and we have sliding vectors. Well, B and B prime, are you okay if I do this? Are the same, and then I change sliding vector if they have same Well, it's the same story up to a certain point. Magnitude, direction, and share the same line of action in Euclidean 3D space. So this is your line of action. It's a specific line in space. This could be your B vector, and the same one up here, B1, I'm sorry, B prime. They are the same vector. Example, what is a sliding vector? What is a vector that I can move on the same line of action and it's fine? You're not going to alter the nature of the problem if you do so. So we agree that the basis is free vectors. As long as I don't change their direction, I can move them around. In which cases can I actually take the vector and I can only move it along the line of action? That's a force. That's fine. You're not going to change anything if you move a force along the same line of action. If you don't, and if you move it away from the line of action, then you're making a mistake. Forces are sliding vectors. They're not free vectors. And then the last one, the most constrained of all, they have no choice other than sticking where they are, is the bound vectors. Bound vectors, B and B prime, are the same bound vector. We can say if they are the same sliding vector, and share the same point of application. It's going to be fun to draw this. I mean, this is my line of action. This is your point of application. This is B. And guess what? B prime is the same. Just I should use a different color, but there's not much you can do with them. A position is a bound vector. You choose an origin. You're looking at a particle P in space. The point of application is bound. Once you've chosen your origin, your reference frame, you don't change it. You stick with it. Otherwise, you'll be crazy changing your origin and redefining everything from scratch. And so that's a bound vector. The point of application cannot change. OK. Now, everything we do is with free vectors. Let's attack. Today I'm going to use a little more my cheat sheets because I want to be consistent with how I code vectors here. Let's start attacking that expression that allows me to relate rates of change of vectors between two different reference frames. Let's make that expression a little nicer and more useful than it is right now. We have already said, I'm going to write this so many times. Get used to this, because this d dt with respect to a frame A equal d dt with respect to another frame plus something else is what we're going to see for the rest of the semester, pretty much. OK, we agree that these are what they are, dA with respect to A, d with respect to B, and then there is this extra term here, which we can manipulate a little bit. Okay. So in other words, I want to be able to compute these dEi in dt in A. I don't know what they are. It's an unknown vector for I going from 1 to 3. But I do know lots of things about these EIs. I know two properties. Actually, I define them, so of course I know them. I know that EI dotted with EI is equal to 1, the unit vectors, right? For every I. That's the first property of a basis. We also know that EI dotted with EJ is 0 for I not equal to j. Magnitude 1, orthogonal vectors. Now when I operate on two vectors and I apply the dot product or inner product in 3D Euclidean space, what do I get? Well, scalar product, so that tells you already. You get matrix, vector. What you get? Scalar, right? I didn't put the underline here. Didn't put anything. This is scalars. So that means that I can take these two expressions and take the rates of change. Not only that, it doesn't matter in which reference frame I take it, it's going to be the same. And since I'm so worried about computing these rates of change in A, well, I'll do it in A. So let's take the d dt in A of EI dotted with EI. That's going to be 0, of course, because the rate of change of 1, and that remains 1 all the time, is 0. So this is going to be, what is this going to be? How do you do the derivative of this? Well, I know it's 0. Can you help me expanding that? EI. It's a product, right? It's a product. EI dotted with d dt in A of EI. Am I done? Plus d dt in A of EI dotted with EI. Can I write this in a better way? What is true about the dot product? You can commute the vectors, it doesn't matter, right? So this is going to be twice, for example, EI dotted with d dt in A of EI. And so basically this property here is going to give me the following expression. Let me write it the other way, it doesn't matter. D dt in A of EI dotted with EI equal 0. And I'll save it here. Now when I said the other time that you should expect some conceptual questions, this could be one where you have to take a derivative and know that the dot product is commutative. I mean, these are tools that you should have, but they could ask you questions like these, of this nature, where you have to do some steps and get to the final result yourself by applying what you know. This is nothing that complicated, but it is conceptual. So the second one, I'm going to do the same. D dt in A of EI dotted with EJ. This is also a 0, scalar. And same story, EI dotted with d dt in A of EJ plus d dt in A of EI dotted with EJ. Can I do anything else about this one? Nope. There are two different EIs here. So I can just say that this is equal to minus this other term, if you like. And so the consequence of this expression here, okay, it's going to be, let's put it this way, EI dotted with d dt ej in A is going to equal to minus d dt in A of ei dotted with ej. So I have these two nice formulas here that I'm going to use. Okay. Now, and this is where I want to be consistent with the way I name things here. Let's see what we have. Now, these d, ei, dt in A, they're going to be vectors, right? Well, first of all, let's think about, well, this doesn't really, I'm not sure it tells me much, but this tells me something. What does it tell me?
That the derivative of the vector is orthogonal to the
vector itself. When it's unit magnitude and it's moving around in space, this ei, it's moving around in space, its rate of change is going to be a vector that at all times it's perpendicular to ei itself. That's only true when ei is of magnitude 1. Again, stop for a second and think about the formulas you have. If they tell you something, that's important to get it out and translate it in words. This doesn't tell me much, but I'm going to use it. Well, it tells me that the dot product between ei and the rate of change of another of the two vectors is equal to minus the dot product of the rate of change of ei and that same vector. Well, it's kind of mouthful to say. It doesn't really help me at all. What I want to do, though, is since those derivatives that I'm trying to find are vectors, well, let's express them in the basis that I have, which is e1, e2, and 3. And so what I have here for you is the following: d dt of e1 in A. Well, let's say that I call it omega 1, 1, e1. Let's see what I've done. Omega 2, 1, e2, and omega 3, 1, e3. And then e2, the rate of change of e2 in A, bless you, is omega 1, 2, e1 plus omega 2, 2, e2 plus omega 3, 2, e3. And the last one is the rate of change of e3 in A, which is omega 1, 3, e1 plus omega 2, 3, e2 plus. I mean, you can call these whatever you want. It's just what makes sense to me to get to the final result. So I can do this, right? The rate of change of EIs are a vector, and my basis, the one that I can use, is E1, 2, and 3. I'm free to write those vectors as with the corresponding representation in the coordinate system I have, even though I have no idea what these coefficients are for now. But that's fine, I can do it. I could have called these A, B, C, D, E, F, G, H, I. I mean, doesn't matter. I call them omegas. Now, let's use these properties here. Well, this is telling me that the rate of change of any of these guys here, E1, 2, and 3, is going to be perpendicular to themselves. So what can I start doing with these expressions that I wrote down? They don't need to remain full-blown projections like these. If this vector is perpendicular to if the derivative of E1 is perpendicular to E1 itself, that means that the derivative of E1, the rate of change of E1, can only be expressed as a combination of E2 and E3, right? Cannot be on E1. That's saying it out loud. If you want, do this. Substitute 1 in the I. If you do the dot product of all these expressions with you dot it with E1, you only get omega 1, 1, that needs to be 0. So 0, same goes for omega 2, 2, same goes for omega 3, 3, and I've used the first property. Okay, then the other one, I actually have to do it. It's not that difficult. Let's use the second one. Let's say that I do E1 dE1 dt dotted with E2, for example. So I'm looking at this, right? If j is 1, so let's say that j is 1 and I is, I don't know, what did I say? 2. So I'm looking at this derivative here. I'm on left-hand side, dotted with E2, only leaves me with omega 2, 1. So I have omega 2, 1 on one side of that equation. Then I go on the other side. I have a minus. Again, I is 2. So dE2 in dt, I'm looking at this second formula here, dotted with E1. So I'm looking at this term here. So that's what I get. Making sense? I'm just applying those two. And so if you keep going, you get that omega 1, 3 is equal to minus omega 3, 1. Omega 2, 3 is minus omega 3, 2. And so I can reduce this expression the following way. Omega 2, 1, E2. I want to make mistakes with the signs here. E3. And then minus omega 2, 1, E1 plus omega 3, 2, E3. And finally, minus omega 3, 1, E1 minus omega 3, 2, E2. I'm calling here, stay on the other side. I don't need these expressions anymore. See what I've done? I defined just omega 1 to be omega 3, 2. Omega 2, I say that it's minus omega 3, 1. And omega 3 is omega 2, 1. I can do that. I can do whatever I want. I'm defining these coefficients. I don't know them. And we define this vector, omega BA. Whoa. Okay. To be omega 1, E1 plus omega 2, E2 plus omega 3, E3. So if this is my vector omega BA, the angular velocity, this is called angular. We're going to comment on this vector for a while. But let's give it its name. Angular velocity of frame B as seen by an observer in A. That's how it's defined. Again, we'll talk about it a little bit, but we're not done yet. So if I look at those and substitute what I have, these omega 1, 2, and 3, I basically see that I don't have space anymore here. Well, I don't want to erase these. Well, let's start noticing that dt in A of V1 is actually omega BA cross with E1. We can prove it. We can just do it if you like. What is going to be omega B1 cross with E1? Who wants to do it? Do it down here. Well, it's going to be omega 1 E1 plus omega 2 E2 plus omega 3 E3 cross with E1. I already see that I don't see any E1s there, which is good. I should not expect any E1s there. And now, since again I'm terrible at cross products and I don't want to do it, I don't want to think about cross products, because that's not the point here. I'm going to draw this diagram here. And that gives me E1 cross with E1, it's a 0. E2 cross with E1. Do I have an error here? What do you think? No? What is E2 cross with E1? Minus E3, right? With what? With omega 2. Yeah, that's right, because I defined omega 3(1) to be omega 2, so that gives me the minus. And then what I'm left with, E3 cross with E1, E2 plus omega 3 E2. That makes sense. The E2 is multiplying omega 2(1), which I defined as omega 3. The E3 is multiplying omega 3(1), which I've defined as minus omega 2. So do the following with the other two, and you basically get that this is valid for each one of them. So I have expressed the rate of change of any of those vectors of the basis, which is fixed in B, the rate of change in A as the cross product between these angular velocity vector, which I've just defined, and the vectors themselves. And it makes sense. I know that the cross product, that the rate of change of EI needs to be perpendicular to EI, and this is a vector which is perpendicular to EI, of course. Okay, so but I'm not done yet. I need to go back to my expression. Can I erase this, right? Remember we had these, d dt in A of B is d dt in B of B plus, let's start substituting what we have. Here I would have dE1 dt in A, so that's omega BA cross with E1 plus B2 omega BA cross with E2 plus B3 omega BA cross with E3. What is true about the cross product? These are scalars again. I can move them around, B1, 2, and 3. But what is true about the cross product? It has some properties. One of them is distributive, right? So that can be compacted in the following way. I can write omega, I can basically collect omega BA, right? And do the cross product with B1 E1 plus B2 E2 plus B3 E3. Any objections? Okay. And I'm done. What is this? That's B. That's B. Okay. D, B, dt in B plus omega BA cross with B. And we're going to circle this. A couple times and give it a name. This is the transport theorem. This is the most important thing that we'll ever see in this class, probably. Well, there are other important things, but without this, we're not going anywhere. Let's think about this formula. First of all, what do I see in this expression? I see vectors. They're all vectors. Rate of change of B in A, rate of change of B as seen by an observer in B, they are vectors. Omega BA is a vector. I defined it to be a vector. B was a vector. That's what I started from. The cross product between the two is a vector. So this is a coordinate-free expression. It doesn't matter that I've used the 1, 2, and 3. That's implementing the problem. I solved the problem, if you like. I got to this final result by using a coordinate system. That was my tool. But the final result is a vector equation, and vectors don't care about the coordinate systems. You can project these. We'll see in examples, of course. At this point, everything is still abstract. But these are vectors, so you can project them in different coordinate systems, if you like. But this is coordinate free. These are all vectors. And most importantly, this is telling me that if I am an observer in B, I can obviously measure this directly, because I can write the vector in my coordinate system. But I can also tell you what is the rate of change of the same vector as seen by another observer, as long as I know this term. This is the difference between what I see and what my friend in A sees. This is the difference. We're both right, but that term needs to be there to compensate for the fact that we are in different frames. So what do I do with this? What is this? There's a few observations we need to make about this angular velocity, because so far I have I've defined it as this vector here with these coefficients. But does it tell me much? Not really. I have defined it as the angular velocity of frame B as seen by A. But it's just a definition. I don't know how to compute it. I don't know what to do with it, right? So let's think about that transport theorem a little more. First of all, I call omega as the angular velocity of B, of reference frame B, as seen by an observer in A. The following is also true. By just changing the sign of that vector, I'm giving you how an observer in B, which is me, what is the angular velocity for an observer in B of the frame A. So they are basically the same vector, except the difference in sign. How the frame A is moving with respect to my frame, well, it just requires changing a sign. But I'm telling you just that. I'm not telling you where is that coming from. Any guesses? So this could be a question, your test. Prove that. How do you prove that?
The fact that they're unit vectors wouldn't have to deal with that.
Omega is a vector. It's not a unit vector. I don't know if that was the comment. The EIs are unit vector. Okay, can we translate in expressions? How do I get to this? I wouldn't do it that way, but it could be another way. I have my own way in mind that I'm going to share with you, but if you have other ways to show it, that's perfectly fine, as long as you can justify it. So E1 and 2 and 3 are unit vectors. Okay, fine. And we said, so basically you're thinking about this expression, I guess. d dt in A of EI is omega BA cross EI. Could you start from there, maybe? What I would do, since what I'm doing here, I'm going from B to A. I can measure this. I want to find out what this is, and I need this piece of information. So I'm going from B to A. This is, I guess, this is my way to remember this expression. I'm going from B to A. Right of the omega, the superscript on the right of the omega is where I'm going, where I'm starting from, and this is where I want to go, right? Well, what about I take that expression and I do the opposite? I am in A and I want to go in B. After all, those are just the names of the frames, right? I do the following. d dt of B in B is d dt of B in A plus, well, now I have to call it omega AB. I'm going now from A to B, cross with B. That's correct, right? So I put it side to side to that expression there. I want to put it down here. B plus omega BA cross with B. Okay, nice. So how about I add them up? If I do the addition of the two expressions, well, these two will go away, right? These two will go away. I'm left with 0 vector has to be equal to omega AB plus omega BA cross with B. Make sense? Well then, unless B is always a 0 vector, which in that case there's no point for us to really take any rates of change, this needs to be 0, right? Which implies that omega of B as seen by A is minus omega of A as seen by B. Okay, that's an additional piece of information. If you have the angular velocity of a frame with respect to another, to do the opposite, you just change the sign. That's nice to know. So that's I guess one property we want to keep in mind. There is another property, and I'm slowly getting to the point of actually telling you how you should really compute, partially telling you how you compute omega, which I know you have in mind. It's the derivative of an angle times a vector, and in most cases it's fine, but not in general. Okay, this is clear to everybody? That's a nice property. So the next one is that, what if I have more reference frames involved? You could have frame A, frame B, frame C. And I can definitely write that dB dt in A is dB. I told you that I was going to write this at least 1,000,000 times before we're done with the class. Omega BA cross with B. But I can also relate B and C. Let's say that dB dt, how do I want to do this? B is d dt of B in C plus omega CB cross with B. I do the same exact thing I've done before. Add the left-hand sides, equal that to the addition of the right-hand side. These two will go away. You get, I really I don't like writing down here. dB dt, can you see down here actually? Okay. Of in A is equal to dB dt in C, wow, time is flying, plus, I guess we'll do an example next time, plus the addition of the omegas, right? Omega BA plus omega CB cross with B. Okay. Well, but what is this? This needs to be, I need to break it. That's omega of C as seen by an observer in A, right? So the other property is that if you have multiple reference frames, you can add the angular velocity vectors. Omega of C as seen by an observer in A is omega of B as seen by an observer in A plus omega of C as seen by B. Does this make sense? That's another nice feature. I need to speed it up because I want to tell you one more thing. Now, how do I compute this angular velocity? 5 minutes. Well, let's start with a simple case, and then we'll continue. Say that I have a coordinate system E1, E2, E3, which is fixed in some reference frame A, and then I have another coordinate system, little e1, little e2, and little e3 corresponds to big E3, which is fixed to another reference frame B. They have the same origin. They can. Two reference frames can share the same origin. Why not? The wheel on your car, the wheel has the origin, if you want, to that frame is the center, and it's the same, can be the same origin for the shaft. They can have points in common, and they can be used as origins. And so this second frame is rotating about the E3 axis, and the angle is called theta. Okay, so say that I want to compute the angular velocity of B as seen by an observer in A. So I want BA. Well, what I would do, since I know my expression d dt, for example, of E1 in A it needs to be some omega BA crossed with E1. I start computing this. And one way to do it is writing E1. I can write E1 in the coordinate system big E1, big E2, right? So E1 is going to be what? Cosine of theta E1 plus sine of theta E2. Do we agree with this? And then if I take its rate of change in A, it's going to be minus theta dot sine of theta E1. I'm assuming that we're all perfectly capable of doing these algebraic steps, which collecting theta dot is theta dot minus sine of theta E1 plus cosine of theta E2. And I'm sure the temptation here is calling this omega BA, calling it what? Theta dot E3. Little e3, big E3, doesn't matter, they're the same thing. In this case, it's not always the case. And that is correct in this particular problem, but I want to show it to you at least for a single axis rotation, one angle case. Because the three-dimensional case actually is based on this. Any generic rotation in 3 dimensions, it's a combination of rotations about single axis. It's just there are intermediate axes involved. And we're not going to do it for quite some time. We're going to describe other angles and how they are defined in the future. But you're fine with understanding that the angular velocity vector in a case like this is the derivative of the angle between the two coordinate systems times the vector, which is the vector of your axis of rotation. If you're fine with this, then you can build 3D rotations. Again, we'll see it along the way, but I want to leave you with this piece of information about omega. Well, let's just prove it. I'll do it. I'll do omega BA crossed with A1. If I claim that that's omega BA theta dot E3, then I substitute it here, and I do cross cosine of theta E1 plus sine of theta E2, and that is going to give me exactly this, believe it or not. It's going to be, theta dot sine of theta. Well, let's do it one by one. Okay, the first one is theta dot cosine of theta E3 crossed with E1 is E2. The second one has an E3 crossed with E2, which is a minus E1. So minus theta dot sine of theta E1. So that's true. For a single axis rotation, simple like that, that's your angular velocity. Prove everything. Give us something as simple as this. I'm not fine with someone telling me the angular velocity for that case is this without justifying it. Well, here it is. It is that vector. And you can build 3D rotations based on that. And I think we don't have time for anything. I will just leave you with this example. This is where we start from next time. I'm going to solve this one. A disk D, center of the disk. We're going to compute the this is ground, if you like, the velocity of P as seen by an observer fixed in the reference frame of the disk and fixed in the reference frame of the ground. We'll start with that. And we'll do it both ways, with the transport theorem, without the transport theorem, to see how different things are, if you use it or not. And then we'll expand to more complicated problems, of course. Questions? Good? See you on Wednesday. Thanks.